to talk about is planning your power measurement and accuracy. So we'll do that, but I'm going to touch on SNMP a little bit, and then this multiplex over AES standard. So, okay, go ahead and go to the next slide. So, some basics: RF power measurement accuracy, or actually more appropriately, the errors that are inherent in making measurements and how they occur and why they occur. Simple network management protocol. I'm just going to do a real brief introduction to that. Most of you are probably more expert about it than I am at this point, but it's something that we got involved with a few years ago, so I want to talk a little bit about that and how it relates to some of our products. And then multiplex over AES. Things to consider with cabling management and loading and that kind of stuff, because we'll do audio here. Okay, next slide. So you should see some sort of a triangle.
Yes, sir.
Everybody see that? Okay. All right, so the title of this thing is really power measurement accuracy, but it really should be power measurement errors and how they stack up against you. So we have a specification like our competitors do for our power measurement products, like our DPS 100D series power meters, that you could expect a maximum error of X. Well, it happens to be plus or minus 5% of indicated reading. So one might wonder, well, how do we derive a specification like that? And that's really what I want to talk about tonight. So at the top of this triangle, we start out with some sort of a standard that everything gets referred to. And in this case, as with many things, it starts at the National Institutes of Standards and Technology down in Gaithersburg, Maryland. So, you know, just about anything that you want to measure, you know, with some sort of a standard, they have a standard for calibration for it. So whether it's a thermometer, a strain gauge, or RF power measurement system, they have a set of standards and a measurement procedure where they can tell you just how close it is. Now, I'm going to just call your attention to some things that are on this slide. If you look over to the left-hand side, you see plus and minus, you know, 1%, you know, up there in parallel with NIFT. And then there's a delta over on the right-hand side, which is just, you know, just adding the two together. Just, you know, it's an absolute value. In other words, you could have as much as a delta of 2%. But let me explain where that first thing comes from. So, the National Institutes of Standards and Technology has developed procedures for measuring RF power or calibrating RF power measurement devices. And that's both sensors and inline devices and things like that. So, at the end of the day, the very best that they can guarantee, that they can tell you that the device that you send them for calibration is to the standard that they use is 1%. So that means that it can't be any better than that. We can't tell you that it's absolutely dead on 0% to our standard. There's a measurement uncertainty that they will tell you is about 1%. So I'm just going to have you keep in mind that you want to be adding up these things along the left-hand side here until we get to the bottom. Now, sending anything to NIFT is actually a very expensive and time-consuming process. I mean, you can do it if you wanted to take your inline power meter out of the line and send it to NIFT. You can do that. They'll run a set of tests on it. They'll tell you how, you know, what the delta is from their standard, you know, within this plus or minus 1%, you know, measurement uncertainty. But you probably wouldn't want to do that and pay for it because it's a very expensive process. I think the last time I checked, it's about $5,000 to do that. So if you take that on top of the cost of a meter, you're, you know, in some cases you may be in excess of what the transmitter cost that you're trying to measure. So, so what to do? Well, we move down the triangle here now to the yellow section where we have lab standards. That's what we use, and that's what our competitors use. And there are a couple of different kinds. I'll just briefly talk about those. Calorimetry is one laboratory standard. Anybody that's worked in television for any period of time, especially in the analog days, is very familiar with calorimetry because that was very often used for power measurement of a television transmitter. And basically the way it works, if you're not familiar with calorimetry, is that you are basically taking calories of heat and converting it to watts, essentially. In other words, you have a flow channel with fluid in it, and you have that attached to a directional coupler of some sort, and the fluid runs through at a particular rate. You have an inlet temperature, and you have an outlet temperature, and the delta between the two temperatures is basically calories of heat, which gets converted into kilowatts. And that works pretty well, but it's not without its issues. You have, let's just analyze this very quickly. If you look at the things that you have to know about, you have to know with some degree of certainty what the thermometer temperature ranges are, and in other words, what those uncertainties are. The purity of the liquid, the size of the channel, the rate at which it's passing through the channel. All of these things have tolerances and subject to error. So that's one type of standard. Now, we don't use calorimetry because calorimetry is typically used under power. So we use a second type of a standard, which is basically a calibrated reference generator. It's basically a signal generator, but it is a very highly accurate signal generator in terms of its guaranteed output. And that's what we use as a standard. Now, these are, as I said earlier, these are secondary standards. And a secondary standard has to get calibrated to something. Well, what do we calibrate it to? We calibrate it to a primary standard, which is NIST. So the calorimeter that you might use or the reference standard that we use is calibrated to NIST standard. So now when you do that, you have to add yet another 1% because, there's something to keep in mind. In power measurement, 0.05 dB is roughly 1%. So if you look at the specifications for a lot of power meters, and you look at, like for example, laboratory power meters that are made like people from Rohde and Schwarz or Keysight or Enritsu, you drill down through the specifications, you'll see that generally speaking, the error for the sensor is 0.05 dB, plus or minus 0.05 dB. Well, that's 1%. So you have to add that additional 1% in. So now we're up to about 2%. And we still haven't built a power meter yet. All we've done is we've calibrated the sensor head that is attached to the directional coupler. Well, let's move down the triangle one more time here. So this is the light green section of the triangle where it says other lab and test equipment / fixtures. Okay, so you want to build a power meter. So you start with an RF sensor, and then you have to attach it to some sort of a directional coupler. And of course, we do that, and we calibrate the entire system. So the next thing you need to do is you need to know that the directional coupler, the coupled port output, has a certain frequency response to it, and it has a certain output level, and you need to know that with a very high degree of accuracy in order to marry that up to the sensor so that you know what the actual power output is. Well, how do we do that? Well, we use a piece of test equipment. It's called a vector network analyzer, where that directional coupler is swept, and we look at coupler loss, but we also look at directivity. And I'm going to talk about directivity as we get into this a little later, after I get done with, I think, this slide or the next is a discussion of directional couplers. Well, all right, we're using another piece of test equipment now. So the vector network analyzer, you guessed it, has to be calibrated to a NIST standard. And if you read the specifications for most analyzers, what's the measurement uncertainty? It's that familiar 0.05 dB, so it's another 1%. So now we're up to 3% error, perhaps. In other words, that's the maximum delta that you might have. But we're still not done. Let's move down one more rung on the ladder of doom here, as I call it. Other effects, such as temperature variability, handling, and long-term effects. Well, we know that any electronics or physical constant, anything that has a physical nature to it, directional coupler is made out of pipe, basically. It's copper, it's aluminum, and some silver plating, Teflon, and other materials that expand and contract with heat or lack of heat. So one has to take into account the physical constraints that you're going to use this equipment in. So temperature range, we've tested our equipment with from 32 degrees Fahrenheit to say 150 degrees Fahrenheit. We know that the delta in the actual power measurement capability is about 1%. In other words, that's the additional error that you might have over that entire temperature range. Now, typically you don't run into that too much because we're going to calibrate this meter probably at the same temperature, and it's going to be operated within the same temperature range as in your transmitter room. Probably going to have a little elevated temperature because the transmission line is going to have a little bit of heat associated with it. There's very little loss in the coupler itself, but you're going to have some heating effect. Then there's some other things you have to consider. Component aging, both over the long term, and then there's the handling. Once the power meter has been shipped to you and it's installed in the line, there may be some slight change in the geometry of the let's say the coupler element to the transmission line, and so these all add up for you. And we've through field experience, we see that this is usually about a 1% additional error. So now we're at 4%. Now we're at the bottom of the triangle, the field comparison of one meter against another. Well, and this is the. Can everybody still hear me okay? Because it got very quiet. I just want to make.
We're good. We can hear you.
Everybody's muted.
Everybody's muted. Okay.
Hello?
The question that we get I won't say very often, but we get it, is, I just bought your power meter. I've installed it in my line, and it doesn't agree with my transmitter. What's wrong with your meter? And you notice how I worded that, because the transmitter manufacturer is never wrong. It's always the power meter manufacturer that's wrong. Well, let's think about this for a minute. The transmitter manufacturer makes the power meter, perhaps, or maybe buys it from someone else, I don't know, and installs it in their transmitter. And all of the discussion we've had up to now about the errors, what do you think that meter and the transmitter is subject to? The same set of constraints and the same set of errors. So now you have two meters that could be perhaps as much as 8 to 10% delta between them. That's that's generally not the case. I mean, statistically, it's somewhere in the middle. But you could have a situation where a meter, an external meter and the one in the transmitter could be 10% different. And guess what? They're both within specification. Now, generally, I get calls like, well, the transmitter doesn't read the same as the meter, and well, what's the difference? And you calculate it out, and it's about 2 or 3%. And that's when I tell the guy, once you go, you probably ought to go clean the filters or something like that, because you don't have a problem here. But these are the things that you have to consider. You have to understand that nothing is ever going to be absolute when you're measuring something. And I don't care whether you take a voltmeter out and you're trying to measure a voltage, or measure temperature or pressure or anything else. There are going to be errors, and they typically will cascade. And that's really the whole story here. So I just wanted to kind of go through this, and so that you kind of have just a general feeling for how we get to where we are here. So okay, I think I'm ready for the next slide.
Okay.
It should be a schematic diagram of a directional coupler. Do we have that?
Yes, it's up.
Okay. All righty. So I mentioned directional couplers, and they actually play a very, very important role. The quality and the type of directional coupler that's used for power measurement is extremely critical. You got to use the right type, and you got to really pay attention to some things. So there are 3 basic types that are listed here. The bidirectional, also known as a balanced coupler, and that's the type that we use most often. I'll define that a little bit here in a second. The unidirectional coupler, which is basically a voltage sample, and that's the typical BNC connector that's attached to an elbow that the transmitter manufacturer furnishes for you to hook your modulation monitor up to. And I don't even think they're any good for that. And I'll explain why here in a second. A voltage sample is basically a small antenna that's mounted inside of the transmission line. It's just a piece of wire. It's not terminated. It doesn't have any, it's just basically picking up signal, which means that its directivity, that is its ability to pick up or reject a signal in either direction is equal. So it'll pick up equally well in forward and reflected directions. And then the third type is the compensated or frequency compensation coupler, which has a network inside of it. So there's probably some sort of a smoothing network and a termination so that the coupler is extremely flat over a very wide bandwidth. Now, we sometimes use these, but we don't often, and there's a reason why. Because the compensated coupler, while they have a very flat frequency response, and in some cases that's really desirable, let's say in a combiner system or particularly a television combiner where you have a pretty wide frequency range, you want to know that the response of the coupler is pretty flat. The problem with compensated couplers with networks in them is that the directivity isn't quite as good as the bidirectional style. So why is directivity important? Well, that's going to be on the next slide. But let me define what the bidirectional coupler is, because that's what we use most often. Schematically, you see here a two-port coupler with a forward sample and a reflected sample. And you note that the forward sample is closest to where the RF is coming from. That's the transmitter, and the reflected sample is closest to where the RF is coming from, the reflection, which is from the load or the antenna. So these are typically installed in combiner systems or in transmitter rooms, and you can use them for general pickup, for modulation monitor, making AM noise measurements, that kind of thing. And you notice there's a termination, there's a resistor there, and that's pretty important to have that termination because that's what makes the balance part of the balance coupler. Okay, so next slide. So just a quickie thing here on second ports. You'll notice that our power meter, which is the electronics part of this, is attached to one side. And what we do is we terminate both the forward and the reflected port in 50 ohms, and we use that one set, forward and reflected set, for the power meter. But you can also have a second port that's available for measurement. And I mentioned directivity, which is the amount of attenuation from one port to the other. In other words, that is the isolation between ports. And typical value for broadcast use is about 30 dB or about 1.06 to 1 VSWR. Why is that important? It's important because if you want to make quality measurements, you want to make sure that the measurement system that you have has sufficient dynamic range to make the measurements that you want to make. It's kind of like audio, in some respects. You want to measure noise in an amplifier. Well, if you want to see that the amplifier has, let's say, a 90 dB dynamic range, let's say it's, I don't know, the noise is 60 dB below, below nominal level. Well, you need an instrument to measure that has a noise floor that's in excess of the amplifier. So you need something with perhaps 100 dB noise floor. It's the same thing with RF. And here's a typical example of what I'm talking about. So let's, you just use, this a lot of words on a page here, so I'll try to explain this. AM noise. And, this is something that used to be very, very critical with vacuum tube transmitters. Maybe not so much anymore with solid state because they're fairly broadband, but you still do want to know what the bandwidth, let's say, of a filter is, or the antenna itself. You want to make sure that nothing between the transmitter and the load is impeding your signal, and that it's symmetrical. And that's what AM noise allows you to do, to measure that on an FM system, for example. So a good spec for AM noise is 50 dB or better. If you can get 50 dB of synchronous AM noise out of a system, you've done pretty well. Now, let's take the example of a directional coupler with a directivity of 20 dB. So that's going to have not quite the greatest isolation. And let's use 10 kilowatts forward power, since that's a nice round number. So that, let's just assume an antenna return loss of 22 dB. Which will return about 63 watts. But remember that the reflected power signal is subject to a round trip time, all right, because it goes up the line, it reflects off, part of it reflects off of the load and comes back down again. So which means that the signal that is reflected is not in phase with the incident signal, the 10 kilowatt measured signal. So if you allow these two to combine, you could have synchronous noise AM of here in this example, you have the directivity plus the actual antenna return loss is going to be equal to the AM noise contribution of the measurement system. So again, we said 20 dB of directivity plus that minus 22 dB of return loss on the antenna, your VSWR. So that's going to come back and it's going to say 42 dB. Well, this might lead you to believe that you might have to start figuring out where that problem is, that you may want to increase the AM noise. But if you wait a minute and you take a look at, and you use a coupler that has an additional 10 dB of isolation, think noise again, you're forcing the noise floor down by another 10 dB. Now you have a noise floor of minus 52 dB, and you can easily measure minus 50 dB resolution with that. So that is why directivity is very, very important. Now, another area where it's important is when you're measuring reflected power. If you're concerned about VSWR, then you've got to make sure that what you're measuring is actually reflected power and not some contribution from the incident port. So it's pretty important. And I think that's the RF section of the of the presentation tonight. So, does anybody have any questions or comments or anything about what I've said thus far?
I think we're good.
Okay. Okay, we're good. All right, so let me keep moving here.
So just tell me what slide to be on.
Management protocol, okay, which is this interoperable standard that we've all kind of gotten familiar with. Most of you by now have had to deal with this either in the transmitter site or a studio site. And I just want to briefly cover some basics about SNMP and how we're kind of using it. And that's what this is all about here. So I don't, again, this may sound a little 101-ish. And if it is, I'd like to know. But anyway, some SNMP basics. Three basic variations of it, V1, V2, and V3. V1 is the oldest version, where communities are set in plain text and is limited to 32-bit counters, and that's pretty much obsolete now because most people are worried about security and that kind of thing, and you don't really want to send stuff in plain text. V2 adds 64-bit counter capability, and it adds read and write communities, which is essentially passwording of gets and sets and that kind of thing. And then V3 adds encryption, and the industry is beginning to look at V3. I think the data industry, the IT industry is kind of looking at this very hard. The broadcast industry, I have to tell you, some of the companies that are supplying stuff with SNMP, very few of them, if any, that I know of, are doing V3 yet. It's a very complicated standard to implement. So currently, we support a V2 standard, which does give you the additional security of read and write communities. So, some more basics here. The MIB, which is the Management Information Base. How many people knew that right off the cuff? I always have to read it because I never remember what the hell it means. But basically what it is any piece of equipment that's manufactured or any software that will support SNMP has to have a MIB so that you know where to find information and you know how to find commands and status and things like that so that you can do something with it. So it's basically a text file, and it just has a bunch of stuff, a bunch of information in it, coded in a certain way that your machine and software can interpret. So it's a database file supplied by an equipment manufacturer or a software developer that contains all the relevant information, which is what I just said. So they're handy. We have, right now, I think we're up to about 4 different MIBs, but that's over our product categories. And so, for example, we have one MIB for our audio toolbox family, which is our audio switcher router product line. And that one MIB carries, can be used for about 30 different variations of the 3 product subcategories within that product line. So once you've got it written, you can just you can add products to it and make sure that it adheres to the same set of commands. So we use the MIB to tell third-party remote controls and software, including our own BDI Stack software, which I could have demonstrated tonight if I could have brought my computer up, but that's okay. You can download that off our website for free. And basically, that's how it works to control and to monitor things. So there's some more three-letter things to remember here. The OID string, which is the object identifier. And basically, this is an address to identify various functions and how they perform them. And I thought this was kind of interesting that, to pick this apart and describe what these numbers mean. And this is just about every OID string starts out with the same set of digits, and you'll see why here. In other words, you have your 136141. Well, these are the listings of why they are basically all the same. 1 defines it as an ISO group that established the OID standard. 3 is the organization specified text. The 6 means the Department of Defense got themselves involved because they established the internet, much to the chagrin of Al Gore, who thought he did. The 1 specifies that its communication is via network or internet. And where are we letting out here? 4, device was manufactured by a non-governmental agency, a private company. So governmental OIDs have a different, I don't know what the number is, but they have a different number, so it's a governmental system. And then the last one there in that first group is the device manufacturer is classified as an enterprise. So then the next thing is a group of 5 digits, which is the specific company ID. So every company that is doing SNMP and has MIBs has to have a specific ID that identifies that company. So 37691 is BDI's company unique ID. And then once you get to the right of your company ID, this is basically the meat and potatoes of what this OID is going to do for a particular piece of equipment or software. So in this example, I just picked an OID string from one of our MIBs, and basically, I guess what this is the SWP product line, which is our motorized switch controller and our remote control. It's the product. This is the OID string that tells you when you connect to it that you're connected to an SWP 200 or SWP product family. But these numbers, as you see, they kind of stagger down here, and there's a reason for that because on the next slide I'm going to show you, it's going to look like a Windows Explorer, looking at various folders and whatnot. There's a registrations folder, that's the 2, and then within that, the next 2 is our product categories. There's analog, RF, etc. In this case, it's 2 because it's an RF product. The next line, you have a 1, BDI RF product line, RF products. Why there's 2, I don't know, but we decided to do that. Then the next one is the SWP product MIB. It identifies that MIB as the correct one to use, and then the next one is the let's see, what is this? The unit information, fixed information for this particular unit. It may come back with a specific model number depending on that number, and then this is the SWP product ID, which is the last one. So every OID string works the same way. The numbers, those right-hand numbers, are going to shift around. They're going to change based upon what that OID string is used for, whether it's for a set command or a get command or whatever. Now, gets and sets and all that kind of stuff. So some more definitions. A get is like an interrogation. You send this by SNMP manager, and you're attempting to get information from a particular device or other piece of software. So you're sending this command to say, hey, what's going on here? What's how much voltage is there, or how much current, or is this set to 0 or to 1? The response that you get back is the agent sends a response and replying to that GET request. It provides the SNMP manager with the variables that were requested originally. So it's basically, here's what I want to know, and the thing comes back and says, here's what you asked for. It's very simple. A GET next is the SNMP manager sends this message to the agent to get information from the next OID string within the MIB tree. So in other words, it does it in order. And you can do that. You can just keep hitting get next, get next, get next, and it'll tell you every little piece of information about that unit. A get bulk is where you do it all at once. The SNMP agent uses the get bulk message to pull tables of data by using lots of different get next commands all at one time. So you can get the whole table at one time, then you can scroll through it. A set command is just that. It is a command. You can actually do something with a set command. A set is a message sent by SNMP manager to the agent to change configurations and issue commands. So you can turn things on and turn things off and like that kind of thing. Then the trap, which is an alert. It's like an alarm sent by the SNMP agent to notify the SNMP manager when an event happens within the device. Now, I've been talking about agents and managers, and I haven't defined what they are. Well, the manager is kind of like the boss. It's the thing that's in control. It can ask for stuff. It can command stuff. The agent is simply the thing that's out there saying, I'll do what you tell me to do, and that's it. Now, all of our equipment, every piece of hardware that we make is an SNMP agent. The manager are our various apps that we use, or the DDI Stack software that can actually send these commands and get the information back. So that's the difference between a manager and an agent. Simply that. Well, I talked about this stuff already, so we can actually skip this slide.
Okay.
Where I am right now is the difference between get commands and traps. I just wanted to show a brief example of something that you're all familiar with NIB browsers. There's something that are a very handy tool to use, and we recommend one that's made by a company called iReasoning. So iReasoning.com, you can go there, you get it's a freebie, you can get that, and it's really very handy. What this thing allows you to do is it allows you to go in and interrogate agent devices, and it acts as a manager, so that you can go in and you can get gets and sets and do all that kind of stuff. So this is what an OID string actually looks like. And in this particular case, it's a little hard to read this, so I'm going to tell you what this is. This particular OID string is for our SWP 200 motorized RF switch controller to turn the RF on or off, turn the transmitter on or off. And you'll notice is the OID string, data type is an integer, and then the value is what we define as a manufacturer to say, what digit you have to put in. It's an integer value. So 1, you would enter a 1 there for RF off to turn the transmitter off, or a 2 to turn the transmitter on and hit OK. So essentially, the manager, when you have a TX on button, that's what it's doing. It's saying, oh, let me go get that OID string, and we'll send it a 1, because that means you want to turn it off or turn it on. Okay, next slide. This is what the browser looks like. It's a little hard to see this, unfortunately, but the idea here is that it looks very much like a Windows, file explorer thing, and that's really what it is. The MIBs are set up where things are tucked away in file folders, and the various things that you're going to do are there, and you can click on them. And then over to the right is basically a get bulk of, it looks like an SWP 300, which is our remote control system. So everything you want to know about that remote control is on that list, and you can actually highlight it, and you can click on it, and you can do a get to get status of that particular parameter, whatever it is, or to do a set if you want to change the state of that parameter. Okay, just really briefly to close up on SNMP, as I mentioned earlier, this is the BDI Stack software that you see on the left-hand side, which is something that we develop for most of our products. We're kind of getting away from this. We still offer the stack. It's still available, and you can download it from our website, and it works with all of our products. But we're getting into more product-specific apps that, again, work via SNMP. That's how they work. They're just a very small resonant piece of software that resides on your computer. You start it up, and you can interrogate and control any of our SNMP active devices. It includes our switch controllers, our remote controls, and our audio products, and even our power meters. Okay. Next slide. You should see a motorized switch. This is just showing all the interconnection that you can do between. You'll notice that there's our competition's remote control there, the Burkhart Touch Plus. Our stuff works with their remote control just fine. You can interface everything you see on this page here to a Burkhart Touch Plus through a DDI product, either by SNMP or in the case of the the motorized switch there. That's a cable that just connects to the switch. There's no SNMP about that switch at all, but you can connect to our controller, and then you can get to it through the BERC if you need to. Okay, next slide. I think that is it on SNMP. I'm going to move through this very quickly. Multiplex.
There's a picture of our presenter, by the way, just in case anybody was wondering what Bob looked like. We have your picture up.
I call that bookend antiques. Me on the right and that 500 series oscilloscope on the left there with the butterfly pattern. So, okay, I'm going to try to move along here very quickly. Unfortunately, this is my favorite subject because I'm basically an audio guy at heart. But anyway, there's recently a new standard for passing FM stereo. Actually, there's even one now that supersedes this. That is FM stereo over IP. This is specifically about the multiplex over AES standard, which is basically an audio standard. That's coming out of the back of the processor and going into the transmitter, and it's all encoded for FM stereo, and the transmitter does the decoding back to analog and puts it on the air. So there are some things that you need to consider when doing this. We're finally in the radio business. We're dealing with higher sample rates than 48 kilohertz. Previously we were kind of used to 32, 44, and 48. And now all of a sudden we're jumping up to 192 kilohertz. And I'm here to tell you that it doesn't work the same way as those slower clock speeds. And you can have some inherent problems built in if you're not careful about how you manage this. And that's what this is about here. So next slide. This is basically just a chart that defines the bandwidth that you're going to need for certain sample, for the certain sample rates and your unit interval. So if we look at this, 44.1 has a system bandwidth requirement of about in the middle there. You'll see system bandwidth is about 28 megahertz. Yeah, that's megahertz. And then if you go down to 384 is ridiculous. It's 245 megahertz. Well, let's look at 192 because that's the one that we're interested in here tonight. 122.88 megahertz. You might say to yourself, well, why the heck do you need VHF bandwidth to pass an audio signal? Well, because this audio signal is RF. Because if you look at what you're doing, you need to have this is a system of square waves. Okay, and square waves need a lot of bandwidth. Why? Because they're harmonic rich. And you need two things. You need bandwidth and you need phase linearity within the passband. And so these are two very, very important aspects of what you need to have. So we've had a big jump up. You need it's almost about fourfold, almost fivefold increase in bandwidth requirement for 192 kilohertz to do it properly. Okay, next slide, please. So real quick, these are the styles of cables that have been used for digital audio over the eons here. Good old 8451. People cheat and used to use that all the time, which is basically an audio cable. You really shouldn't do it, but it works, but it's not a good idea. Well, then there's the Belden 1800F standard, which is basically a digital audio cable. It was designed to be 110 ohm balanced shielded standard, and it's digital audio cable. That's what I'll say about it. And then the third standard is the Belden 1694A standard, which is basically HDSDI, otherwise known as RG6 cable. And you'll notice it's coaxial. Next slide, please.
Mm-hmm.
Now, okay, so we got involved in this little project a few years ago when a customer bought one of our audio switchers that passes 192 kilohertz. And bought the unit, we shipped it to him, and about a month later, the guy called me and said, hey, I'm trying to do this multiplex over AES thing, and your switcher's not passing it. So I said, really? I said, we test every one of these that goes out of here at 192 kilohertz, run signal generator through on every sample rate, and kind of not understanding that, but he explained to me what he had. He had a Brand X exciter, stereo generator feeding into our box and then feeding into a transmitter, and it would work some of the time, and it didn't work some of the time, and there was just a lot of problems. So I said, well, you know, I don't understand this, but let's see if we can't duplicate what you've got. So with the help of one of our dealers, Broadcasters General Store, I got them the processor manufacturer and send us a processor, the same one that the guy was using, and we got a low power transmitter of the same type and interface that he was using, was an Autel transmitter. And we set it all up, connected everything up using 110 ohm terminations and XLR connectors on our unit and on the transmitter and on the stereo generator. And lo and behold, if the guy wasn't right, it really didn't work very well. I said, this is very puzzling. As it turned out, the problem was not so much our unit; it was the load at the other end. It was not happy with the kind of crummy looking signals. If you look here in this picture, you see these two scope pictures. And I apologize, they're not all that clear, but this was done kind of in a hurry. On the left-hand side, there's 30 feet of 1800F. That's that balanced 110 ohm cable with XLR connectors. And this is 30 feet, it's terminated with 110 ohms. And the signal generator we use is an NTI digirator, as you can see, 24 bits at 192 kilohertz sample rate. And look at what it looks like. Lots of jitter and a lot of overshoot. Now, replace the cable with 30 feet, same length of 1694A RG6. Now, look at the difference. Virtually no jitter. Now, there is some rounding, and I have to, for all, what happened here was that the scope actually was a little under bandwidth. It's a 100 megahertz scope, analog scope. Probably needed a 250 meg scope to do this, but I took these pictures very quickly. But you'll notice that there's no overshoot. It's rounded, and that rounding is the bandwidth limitation of the scope, but very, very little overshoot. So the coax makes a big difference. Well, why is that? Well, let's do a little bit of real basic audio engineering here. The coax has essentially a linear group delay response, okay, and that's what you need. So this is an example of a 100 hertz square wave, 100 hertz square wave, and it's passed through a Butterworth filter, 4-pole Butterworth filter, 1 kilohertz low pass filter. Now note the overshoot. It's approximately 1 millisecond duty cycle, or about 900 hertz. Take a good look at that. You notice the overshoot looks like a sine wave. Well, in essence, it is a sine wave. What that is that's the 9th harmonic that's not lining up in time with the other harmonics. And that actually is a telltale where the 3 dB point of the filter is being reached, where the phase rotation is such that it's so out of phase at this point that when it returns to the source, it's piling up because it's not lining up. It's popping out on its own, and that's what's happening here. So this is just the same thing, and looking at the time domain and frequency domain at the same time. On the right-hand side, you see that the square wave is made up of various harmonics and amplitudes. What you don't see there is the phase shift, and of course you see the overshoot on the left-hand side. Okay, so now this next slide shows a Bessel response, which most of us know is a linear phase response. It has excellent step response, and the Butterworth response. The Butterworth is the red, and the green, which you really can't see all that well because the red is kind of obscuring it, is more like a square wave. Well, what's happening there? Well, the Bessel response, the group delay is flat. There's an equal speed at which all the signals, all those harmonics are passing through the pass band. And that's what you want. Okay, so now this we did here is we took coax and we showed two different processors. Actually, we had a processor A and processor B here, and you notice there's a little bit of a difference in the waveforms, but when you use the coax, they both behave pretty well. Okay, that's the slide is another picture. Now we're going to go to the next slide. And I guess I'm near the end here. So this is our recommendation for multiplex over AES is very simply, we do not recommend that you use 110 ohms. We recommend that you use coax, that you do transformation down to 75 ohms as soon as you can, and then you pass your signals over 75 ohm cable. Because you can do that. I won't say you can do it with abandon, but you can do it for a lot longer distances that have better performance than you're going to have with 110 ohm cable. So we say that you should really avoid it. Keep your cable lengths as short as practical, and use high quality transformers like Canary or or equivalent. And of course, we make a product that has a 75 ohm interface. It's our AES 400 series that you see there, switcher DA product that we've been making for some time. Okay, so now a few quick things, and I think I'm nearly done here. I wanted to just tell you a little bit about some new products that we're working on. Got to sell a little bit of soap here while we're at it. This is our new SWP remote control system. This is what we developed. This is a single rack unit SNMP agent remote control system that has a motorized switch controller, or one or two actually. You can get them in two models, a single switch or dual switch controller, built in. So all that in one rack unit. And then if you need more channels than the base unit has, we have this expander panel, it's called the IOX24, which you see there, which just plugs in. So we have a real remote control now that we think is on par with the competition. And we think we have some advantages here because we've combined the operations of things into one box. You can get remote control, you can get a motorized RF switch controller, and a direct interface to our power meters as well. They connect up to this system, and it doubles as a power measurement display as well. And that's pretty much it. I'm done. I would have had a little more show and tell here if I was on camera, because I could have done, we have some things here in the shop I could have shown you and that kind of thing. But that's pretty much it. How did I do on time?
You did good considering, our challenges with the technology here tonight. So thank you very much.
Well, one thing I'd like to add is check out Bob's website, broadcast-devices.com. He's got some live demos on the site, some little YouTube videos on some of the new products. I know because I put them there.
Yeah, I was going to say Jeff is being very modest because Jeff actually designed our website, did a great job on it, and he's basically been managing that and our Facebook stuff and editing our videos and that kind of thing and that kind of stuff. Got that all set up, so he does real well with that. So we appreciate that help.
Thanks, Bob.
All right.
Right. Well, with that, I will.
I'm here every day, so you know where to find me.
Yep.
Our website is, as you see, is there right on screen, and you can always get me through the website. You can always send an email through there if you don't have my email, but it's bob@broadcast-devices.com, same as our website. And be happy to talk to you about anything that we do and any problems you might be having, or maybe we can have a solution for you.